We're going to talk about hypothesis testing. Hypothesis testing is particularly important in the realm of statistics. We're only going to cover one particular type of hypothesis test, the one sample mean z-test, but there are actually lots and lots of different hypothesis tests. The one sample mean z-test takes one sample, as you might guess, and it looks at the average or the mean of that sample, and it tries to make some prediction based on that sample mean of what the overall population mean might be. And so that guess is the hypothesis. And then the z-test part of it means that we actually will know the population standard deviation. If we did not know the population standard deviation, it would be a t-test. We're going to look at one particular example to see what a hypothesis testing problem is like. And I tried to select an appropriate example, something you might be interested in. We are going to make a guess that the average online statistics final grade is going to be more than 60%. So the average grade would actually be a passing grade, something greater than 60%. Our guess that it's going to be greater than 60% is a hypothesis, and it's actually the alternative hypothesis, which might be counterintuitive that our main guess is going to be the alternative hypothesis, but as it turns out, the null hypothesis, the other hypothesis, is always that the mean is equal to a particular value. And because it's exactly equal to a particular value, we're never really completely able to prove whether the null hypothesis is true. And for that reason, the only things that we're able to prove are the alternative hypotheses. And there are three options for the alternative hypotheses. We've used a greater than option here for our alternative hypothesis in this particular problem, but you could also have a less than, so we could have hypothesized that the mean was less than a particular value, and you could just have simply not equal to. So those are the three different options for alternative hypotheses. Also, we have significance levels. For this particular example, we're going to assume a 5% significance level, and that's pretty standard across statistical hypothesis tests. 5% is very common. You can also have a 1% or a 10%, but 5% is the most common. That seems like a very low value, especially coming from just having done the confidence intervals. But this 5% is actually associated with the significance of the null hypothesis. And remember, we can't ever prove that that null hypothesis is true, so it turns out that when we have values that fall under the 5%, less than the 5%, that's when we prove that our null hypothesis is not true and our alternative hypothesis is true, and so that means that we have a very significant alternative hypothesis. And that means we have a very significant level that's associated with the probability that the alternative hypothesis is true. So now we're going to look at the one mean z-test as described by Neil Weiss in his 7th edition of the Elementary Stats book. In this particular approach, he has outlined a 7-step process to complete the hypothesis test. And we are given, for this particular test, 3 different assumptions. Our 3 assumptions are the same assumption we should have for every single hypothesis test, is that we collected a simple random sample. Also, number 2 is very common for hypothesis tests. We have either a normal population or a large sample size. And what that ensures is that our distribution of sampling means is normally distributed if we have one of those 2 things. And then our 3rd assumption is that the population standard deviation sigma is a known value. And that is because we have a z-test and we need to know the population standard deviation in order to do the z-test. If we did not know the population standard deviation, we would need to do a t-test. So then let's go over the 6 steps. The 6 steps are that the null hypothesis, we need to say what the null hypothesis is, and we need to say what the alternative hypothesis is. The null hypothesis is always that the mean is equal to a particular value, and we call that mu 0. Well, our example assumed that the mean was greater than 60%, that's the alternative, and so our null hypothesis then needs to be that the mean is equal to 60%. And our alternative hypothesis is that the mean is greater than, mu is greater than our 60%. And we could have had a mean that was less than or a mean that was not equal to, but that's not our particular example. But in other z-test examples, you can easily run into that. And then the step 2 is to decide on a significance level, and we were also told that our significance level was 5%. Our alpha value is always a number between 0 and 1, so 5% corresponds to 0.05. Step 3, we compute the value of the test statistic z, and that's a computational type thing. So steps 1 and 2 are pretty easy. You get it straight from reading the problem. With step 3, you've got a little more involved. You need to find x bar, mu 0, which we already know mu 0 is 60%. You need to find sigma, the population standard deviation, which should be given to you in the problem, and we need to have n, the sample size. As of right now, we don't have any of those things, but we will in a minute. And then step 4 is to compute the actual p-value once we have the z-scores. So we will use the z-scores to compute the p-value. We have 3 different types of p-values, 3 different ways to compute the p-value. We have a right-tailed test because our mean was greater than mu 0. So we will be using the right-tailed, but if you had less than, you would be using this left-tailed, and if you had not equal to, you would be using a two-tailed test. For the not equal to, it turns out that your p-value is spread over 2 places. Here you've got the negative of the absolute value of z, and so that's one place, and then if we went out to -5, then this area we could say is the area between -5 and negative of the absolute value of z, and this blue value is the area between the absolute value of z and +5. And so we can use our normal CDF calculator function, and we put in to find the area between -5 and negative absolute value of z for this part, and then absolute value of z +5 to find the area of this part, and we add those two together. For the left-tailed test, it turns out that the p-value is the area under the curve that's between -5 and z, and as you might expect, for the right-tailed test, the p-value is the area under the curve between z and +5, which we can find with the normal CDF function. Once we have the p-value, which we would compute using the normal CDF, and the z that we get in step 3, then we're going to compare p to our alpha value. And we know our particular alpha value is 0.05, so we would see if p is less than or equal to 0.05. If that happens, then we reject the null hypothesis. If that doesn't happen, well, that would mean that p must be more than our alpha value. If p is more than our alpha value, then we do not reject our null hypothesis. And then step 6 is the last step, and it's the interpretation step. So you can do the math, that's all well and good. It's really great that you can do the math, that you can work through the math. If you can't interpret what it means to reject or to not reject the null hypothesis, then everything you've done is fairly useless. You really need to know what it means when you say, I reject the null hypothesis, or I don't reject the null hypothesis. So we'll spend some time working on what that means. It turns out that if we do reject the null hypothesis, then we accept the alternative hypothesis, and we're able to make some statement at the whatever % significance level. We can conclude that the alternative hypothesis is true. If we do not reject the null hypothesis, though, our statement becomes a little more wishy-washy because we can't really conclude anything. We never really say that the null hypothesis is true because equaling an exact value is just impossible to prove unless your sample size is the entire population. So we just sort of give little wishy-washy statements when we do not reject the null, and we'll go over that in our particular example. So what do we need to know? We need to know mu0, and that's our guess, our hypothesized mean, what we think our mean is greater than, less than, or not equal to. We also need to know the null hypothesis, we need to know the alternative hypothesis, and we need to know our alpha value, or our significance level. We already know those four things. We also need to know, and we don't know it yet, our population standard deviation, sigma. And we also either need to know the sample data, and the sample data would allow us to compute x bar and find out the n value, the sample size value, or we need to be given those things. And we will be given all of these things. Let's suppose we're given a population standard deviation of 29, and then we would either be given the sample data set or we would be given x bar and n. If we're given the sample data set, we can compute our own x bar and n. Now let's do the hypothesis test problem by hand. We're going to go steps 1 through 6. Steps 1 and 2 are fairly intuitive. We actually already know what the null hypothesis is, what the alternative hypothesis is, and what our alpha values are, and they're written here. And then we would need to compute our z-score. We need to find z. We already know the population standard deviation that was given to us on the previous slide. Also on the previous slide we were given x bar and n, or we would have been given the data where we could calculate x bar and n. And because we know the alternative and the null hypotheses, we also know mu0. And it turns out that's all we need to know to compute z in the third step. Because z, the equation for z, is x bar minus mu0 divided by sigma over the square root of n. So x bar, that is 61.37. Mu0, that is 60%, or just 60. Sigma, that is 29. And n is 30, so the square root of 30. Now if we're putting this in the calculator, we can put it in the calculator all at one time, but we need to use parentheses so that our calculator knows that all of this is in the numerator together and all of this is in the denominator together. When we compute the z-score and we put all of these numbers into the calculator, we will get 0.25875. And that is our z-score that we will use. The next step is to actually find the p-value. We know from the beginning that our alternative hypothesis is that the mean is greater than 60%. And so because of the greater than, we know that this is a right-tailed test. And recall from the previous slide, we just computed our z-score. And so we will have a picture that looks like this. Our z-score of 0.25875 will fall between 0 and 1, a quarter of the way between those. And then the area, because it's a right-tailed test, the area to the right is going to be our p-value. And to find the area to the right, we would go out to 5 and find the area that's between 0.25875 and 5. And using our calculator's normal CDF function, that's just putting in the minimum value and the maximum value that we want to find the area between, and that will give us 0.3979. So that's our p-value, 0.3979. And it turns out in step 5 we're going to decide whether to reject or not. If p is less than or equal to alpha, then we do reject. So now we have a p that's greater than alpha, so it's not less than, it's not equal to. In that case, we do not reject the null hypothesis. And then we come to interpretation. Interpretation depends on whether or not we reject the null hypothesis. When we do reject the null hypothesis, we get to pretty much accept the alternative hypothesis as true. When we don't reject the null hypothesis, that's when we get to make the wishy-washy statement we're about to make, and here it is. At the 5% significance level, we have insufficient data to conclude that the mean stats grade is more than 60%. So we're really not saying anything there. We're just saying there's not enough data to know. And so we're not going to conclude anything. To construct your interpretation, you need to tell us what the significance level is, because if this had been a different significance level, a different alpha value, then we would have in fact not rejected the null. We would have rejected the null. So we would have done the opposite. But that's why you need to really tell us what the significance level is. So here we have a 5% significance level. And then here, because we did not reject, we say we have insufficient data to conclude. And we want to tell what we're concluding or what we're not concluding. And that's usually a statement of the alternative hypothesis, because we would only conclude that the alternative hypothesis was true. So this last part of the interpretation is almost always a rephrasing of the alternative hypothesis, and here it is: the mean stats grade is more than 60%, which is what our alternative hypothesis essentially is. If we had rejected the null hypothesis, then we would have exactly the same statement, except we would cross out have insufficient data to, and so that would be gone, and we would say instead we can conclude that the mean stats grade is more than 60%. We can actually use our TI-84 calculator to do the steps 3 and 4 of the hypothesis test, that computational part. We can do all of that on the calculator, and our calculator will just give us the z-value and the p-value, and so let's go do that. The first thing we need to do is to put the data into L1, so let's take a look at our data. Okay, here are our data values, and we want to enter them into L1. So to do that, we would press Stat and then Edit to get to the list. And then there is L1. If we did not have the data already entered, we actually already have it entered, we would press 30 and then Enter, and then 39 and Enter, and 82 and Enter, and so on and so forth until we had entered all 30 data values into L1, and then we would continue with the rest of the steps. So now that we've got our data entered, the next step is to go to Stat and then scroll to the right to Test. And these are all the hypothesis tests listed here. We want to use the z-test because we're doing the one sample mean z-test. And here we are, and we actually want to use data. Remember that our alternative hypothesis was that the average stats grade was greater than 60%, so that makes mu0 be 60% or 60. Also remember that we were given the population standard deviation sigma of 29, so that's that value. If we hadn't entered it, we would just enter 29 and press Enter. Our list is L1. If we didn't have L1 written here, we could just do the second key and 1 to give us L1, and then we have a frequency of 1. And then our alternative hypothesis. We select the sign that matches our alternative hypothesis. Again, that is the mean is greater than 60, so we want to select greater than, and we would press Enter, and then we select Calculate and Calculate. And we got a z-score of 0.2581 and a p-value of 0.398. And so if we were doing this problem by calculator, we would just wrap up by deciding whether or not to reject the null, and that would involve comparing p to alpha, and here p is really big, so it's going to be more than alpha. and that means that we do not reject the null, and then we would interpret, and that means that at whatever percent significance level we have insufficient data to conclude that blah blah blah, whatever our alternative hypothesis says. Let's suppose we had the statistics, the sample statistics. That means in this case the sample mean and the sample size. We wouldn't have to go through all that trouble of entering the data in that case. We could just go straight to Stat and scroll to the right to Test, and then choose option 1 because we're doing the z-test, one sample mean z-test, and we would choose the Stats option. And then we would scroll down to mu0, and that would be 60, and our population standard deviation, which we always have to have for the z-test, that's 29, and then we would enter our x bar, and remember that when we were given x bar we were actually given 61.37, so 61.37 is what we will enter here, and then our sample size we are given as 30. Our alternative hypothesis is still greater than mu0, so we leave that and we highlight calculate and press enter. Again, this gives us our z-score 0.25875 and our p-value 0.3979. Notice how when we use the 61.37 we get much closer to the z-value that we obtained by hand and the p-value that we obtained by hand. Again, even if we're doing this test using the calculator, we've still got to be concerned with our steps. We've still got to state the null and the alternative hypothesis. We've still got to state the alpha value. We've still got to, based on what our calculator says, provide the z and the p values. We've still got to tell whether p is less than alpha, more than alpha, equal to alpha, and then based on that decision whether or not we're going to reject or not reject the null hypothesis, and then we've got to give our interpretation statement. So we've still got to do all of those things even though we're using the calculator.